Okay. I'd like to welcome you to the Physics Colloquium. Today, we're very fortunate to have Professor Garth Ilingworth, who's currently a distinguished professor emeritus at UC Santa Cruz. So Garth got his PhD at Australian National University. He then came here to Berkeley and was a Miller Fellow. After that, he joined the staff at the Kitt Peak Observatory, and then went to Baltimore and became deputy director under Ricardo Giacconi for the Space Telescope Science Institute. He then moved to Santa Cruz, where he pursued his career. He's won several prizes, including being a fellow of the American Astronomical Society. And Garth, as he will explain in his colloquium, really played a seminal role in the creation of the James Webb Space Telescope. And I had the privilege of being able to serve with him on a committee, which he's been on many, involved with James Webb. But this was for the Space Telescope Science Institute, trying to make sure that the Institute would be prepared to analyze the data that would come down. So that was an enjoyable experience. So now I'd like to turn over the table to Garth.
Okay. Good. Thank you very much, Chris. Good afternoon, everybody. It's great to be here. Yeah, so I drove into campus and I thought, wow, I recognize this place. But I was here 45 years ago as a Miller Fellow. So I've been here, obviously, since then, various times, especially working Keck. But it is just nice to be back here, and it brings back lots of good memories about those days. So I am going to tell you about James Webb. I'm going to concentrate on the telescope. I was hoping I would get to some of the science at the end. We shall see. There's a lot to be told on this great story about this amazing telescope. And one of the things I did want to mention was that this is a joint and international project. NASA, the European Space Agency, and the Canadian Space Agency all played pivotal roles in making this come to fruition. And so I just wanted to make sure I didn't forget that as I go through the talk. So I think probably everybody here saw this early image of this cluster of galaxies. This was actually shown at the White House the day before sort of the official unveiling of the images. This was the first early release observation. And it was a fabulous image. And it was really aimed at what the goal was. Oh, Chris, do you think another set of lights? Yes, yeah, because it's hard to, it does lower the contrast, you're correct. And so for well over 2 decades, the key or the frontline goal for James Webb, NGST, Next Generation Space Telescope, and then James Webb was this first light, first stars and galaxies. I'll comment a little more on this later. So it was interesting. When I saw this image, I thought, looks fabulous, but it actually looks a lot like the Hubble images. So is it really showing how good Webb is? And then I looked at it a little more closely, and I looked at the detail and the information in this, and I realized, oh my God, we're in a whole new regime here. And it was because this also is just 12 hours. And the ones I was thinking of were hundreds of orbits on Hubble, which sort of visually look comparable. So, as I said, the ball game had really changed with this image. So, what I would like to do is really walk you through how we got to where we are now. And I'll do it in several stages. One is I'll tell you a little about Webb itself, so you get a sense for the telescope and the capability. Then I want to go into the period around launch and commissioning, which was an absolutely crucial phase, of course, in bringing this telescope online. Then I'll back out and I'll go through and talk you through the history and some of the major events that defined this mission. So let me just start out with this rather busy slide, but just to really point out, there's a hot side. It's almost like 2 spacecraft here, 2 different missions, as it were. There's a hot side, which sort of room temperature-ish and above, and a cold side. So the astronomy bits are up here, the telescope and the instruments. Here is all at the bottom on the spacecraft is the control systems, the pointing systems, the power systems, the communication systems, and of course the cryogenic cooler resides there for the MIRI instrument. So this is essential for the functioning of this. The two different distinct entities separated by this amazing sun shield. So just to give you a sort of sense of what we have here, we have a million SPF sun shield in there here, 200 kilowatts of solar radiation incident on the hot side, as it were, and a few milliwatts is all we can tolerate on the cold side if we're going to cool down to 40 degrees K against the microwave background, or actually a mixture of microwave background and zodiacal light. So just to give you an idea now of the astronomy side, as it were, so here is the telescope schematically and the instruments. This is a beautiful design. It's a wide field, well-corrected design, a coarse 3 mirror and a stigmat, and it's polished and operates with amazing figure errors, down to tens of nanometers worth of figure errors. And it was tricky, of course, because it had to be polished at room temperature, all those little segments. There's 18 of these 1.4 meter segments, but then they had to be cooled to check the figure, then brought up to room temperature again, tested, polished some more, and brought down. That was so a lengthy process. But the end result is a fabulous optical system here, as you'll see later too. And just let me note, oops, I did it again. Fine steering mirror. This is a crucial little component. I'll mention this later too. So then the light comes out into this instrument package. So 4 major instruments. You see NASA, ESA, CSA all contributed to these. In fact, our foreign partners, in some sense, did a majority of the work on these. These 4 instruments all look at the sky at the same time. They're in different parts of the focal plane. That makes this also particularly powerful. So 1 to 5 microns for the bulk of the instruments. MIRI is 5 to 20 microns, roughly. So here is, let me see if I can get this going. So this is where we are. In L2, the quasi-stable Lagrange point, 1.5 million kilometers further away from the Earth from the sun. And so it does a halo orbit around this quasi-stable point, and it's delightfully stable. It never is eclipsed by the Earth and Moon, and has permanent incident radiation from the sun on it. So this is a great place for a telescope. Planck was here, a number of other telescopes are here. Roman is going out there as well. So this is where we like to be with a lot of these major missions. And so let me just also give you a sense of how we observe the sky. We can observe the whole sky. Now, I brought this little model here, just because I can rotate it around. So assume the sun is over here. So we can rotate this telescope 360 degrees this way. I don't want to drop this nice model. We can tilt it like so, and we can tilt it a little bit this way. But then with all these motions, we can essentially see over a year anywhere in the sky. And so we can cover what we need, though we have, fairly stringent restraints to make sure that we never get any solar radiation. Sun here, no solar radiation ever on this side. And that's crucial since we have such a cold telescope. So let me now just transition. Now you have a sort of picture in your mind of what the telescope is, how we actually got it out to L2 and the steps leading up to the launch. So during the last few months actually, out at Northrop Grumman, where the telescope was being assembled and finally tested, the telescope came together out there and went through a full sun shield deployment. Here's the sun shield deployed out on the telescope as it was going to be flown, or not as it was flown, but as it would be in space, with the mirror wings folded in at the moment. But in this particular test, it would be folded out. So this was the last time the sun shield was fully deployed. And I'll talk more about the sun shield later. This is an amazing piece of engineering. It looks simple, but boy, it is not. And so here is Webb, folded up, ready to go. So every time I saw this telescope down there, it was, oh, this is awful big. So folding it up, and even folded up, it pretty much took the whole of the fairing on the Ariane 5 rocket. There were millimeters in some areas between the edge of the fairing and the telescope. So we needed all the space we could get on that fairly big rocket. So interestingly, we had to get it down to the Ariane 5 launch site, which is in Kourou in French Guiana. And so here we have a $10 billion telescope. We need to make sure that we don't contaminate it in any way. So it's put into this shipping container here, this shipping container, and was shipped out from Northrop Grumman out to the Seal Beach, the Navy Naval Port in Los Angeles, and then the truck and the shipping container and Webb all went on this ship, MN Calibri, which was one that the Europeans used to transport their equipment and rockets and satellites across from Europe. So these guys were used to doing this. And I think, yep. And so this was interesting. This had a $10 billion cargo on. So NASA was a little reluctant to say very much about this mission. But of course, these days, you can go online, just as you can find where Elon Musk's plane is at any point, you can find ships. And somebody found it going through the Panama Canal. So here it is, going through the Panama Canal, so they knew where it was. But nothing was publicly said until it arrived in Kourou. So here is the journey that it took. In the US, we would fly parts of it around in C5s with this same container, but we couldn't fly into Kourou with this, and the bridges and roads weren't suitable for it. We had to do the ship. So here it is going into the European Ariane Space launch site at Kourou. So once there, of course, we were now several months away from launch. We had to verify that everything was okay after it shipped down there. But we had particular activities that we needed to do. One of them was fueling. We needed to actually fuel this up, and I'll talk more about this later. This is absolutely crucial. L2 is a quasi-stable point. We're in a halo orbit. We need propellant to stay in that orbit, and we also need propellant to offset the momentum build-up from the reaction wheels. So a lot of propellant on board, but the goal was only to do 5 to 10 years. If the goal was 10, the requirement was 5. This isn't long for a mission this expensive, so we were nervous about the amount of fuel we had to some level, but I'll talk more about that later. So here it is, picked up again, and every time I saw Webb picked up like this on a single steel cable, I got real nervous, but anyway, obviously it never broke. And it's being lowered down to sit on top of the Ariane 5. And here is the fairing being put over it with not a lot of space around it, being towed out of the building and getting set up at the pad ready to go. And so then on Christmas morning, amazingly, the French unions agreed to work Christmas morning. I'm sure that took a lot of negotiation and probably a significant bonus as well. But anyway, so at 7:20 a.m., off it went, right on the dot. That was the plan, 7:20 a.m., and exactly at 7:20, beautiful, flawless launch. We had 27 minutes to get into orbit to release Webb. That was the time frame. And the mission, and I was in Baltimore. These are the cookies that were there. We were sitting in the Space Telescope Science Institute watching this on the screen and watching the feed from the control center down in Kourou. And the mission manager kept saying nominal. And we would go, yay, nominal, great, everything is going perfectly. It's a very sort of curious word, but that's the word that folks in the space business just love to hear. All the way up, everything was right on the dot. And so then, 27 minutes later, Webb was actually released from the upper stage. Now, Ariane did a really nice thing for us. They had planned for their new Ariane 6 rocket to put a camera right on the top to see the payload releasing. And they decided, I think with ESA help, that they would actually put their camera, they rushed through the production of this camera. This is the first rocket it went on. So we could actually see Webb moving away from the rocket, and that's what this video is. So this shows an interesting aspect of this. So we see, first off, Webb attached to the upper stage, ready to be released. And it's spring-loaded. The giant springs that just pop it away. You'll see that just now. There it goes. So Webb is now moving away from the upper stage. The upper stage and Webb track each other on the sky for a while, so we are fortunate that we can watch this for a while. But at some point, the upper stage is going to be deviated away. We didn't want it following, nobody wanted it following Webb out to L2. But it would give us probably a minute or two of actual video of Webb itself. So the very first thing that happens here, which is absolutely crucial, is the solar arrays had to come out. There's only a few hours of battery life, and so if they did not work, we would have a dead bird. So the solar array deployment was crucial. It was the only fully autonomous activity, and it was expected to occur at 6 minutes. So we were all watching this and going, and the mission control, the commentator down there was saying, well, it looks great, and we probably won't get to see the solar arrays pop out as it moves away, because it's going to be gone by the time 6 minutes happens. And so as we were sitting there watching like you are now, and then, hey, the commentator said, the solar arrays are coming out. And so this was the folks who were down there who should have known what was going on, and we all went, oh, okay. But we're not going to complain. We want these out, and we need them out quickly. And so Webb actually deployed its solar arrays beautifully. Power came up as hoped for, and then Webb could drift away for its next series of activities. And so what was interesting was I was there and I saw the system engineer after the launch, and I said to him, what happened with the solar arrays? Why did they come out at a minute and a half? And he said, beats me. So, okay, well, fine. As it turned out that what had happened was that Ariane Space and the Ariane 5 had been launched with such precision, and as it goes up, it was being rocked, the upper stage was being rocked back and forward to make sure that the satellite was not overheated. It actually perfectly positioned Webb on the direction at the right orientation to head out to L2. And so the onboard software was looking at this and said, looks like I'm perfectly positioned. I don't need to reorient to the solar arrays. Pop, we'll let them go. And that's what happened. So Ariane Space deserve a great round of applause for what they did for us. So then we got into deployments and commissioning. This was a long activity. So I'll give you a sense of that in a moment. But basically, in 30 days, Webb needed to go out to this L2 point and be injected into it. And during that 30 days, we had to make sure that it got to L2 but didn't go any further. So Ariane Space was requested, shoot us towards L2 but not too fast. And we then had 3 burns of the onboard thrusters, 1A, 1B, and 2. And the first one was a big burn, as it were, to actually make sure we got to L2. And it was crucial that we not burn too heavily in any of these things, because we couldn't bring it back. It's not designed to turn around and be slowed down. So either we were under it or right at it, but not over. So it turned out again that since Ariane Space had done such an amazing job on the injection, we're really close to what we needed to get to L2. We had to use only a tiny amount of fuel in 1A, the big burn. And in fact, that meant that we had more lifetime now for the on-orbit burns that are needed to keep it there. And it wasn't 5 years or 10, it was 20. And in fact, it's probably more than 20. So suddenly, we were in a ball game, in a situation where the life of Webb was not going to be determined by the fuel that was remaining on board. And these thrusters, just to mention, also do these 2 crucial roles: station keeping in a halo orbit, which is only a semi-stable orbit, and then offsetting the reaction torque build up from the reaction wheels. So that was a great result, that we now looked like we had plenty of fuel for life, and now we got into the unfolding sequence. And if you remember Mars mission years ago, people talked about the 7 minutes of terror when you couldn't see what was happening. We had 30 days of terror on this mission, intermittent terror. But every now and again, we had to do something, and every one of these deployments, other than the solar arrays, was initiated from the ground and monitored, but there were autonomous activities going on to actually carry them out. But so at each of these points, it was crucial that these deployments fully worked. And the big one that really worried me was the the sun shield deployment. And you'll see later why that was particularly worrying. But everything worked in that 15 days. So at the end of that, we had a fully deployed web, though the mirrors were not yet in position. They all had to be moved with these amazing actuators, 132 actuators on this. They have 10 millimeters worth of range, and they can move in 8 nanometer steps. And so they had to not only macroscopically move away from the launch stops, they also had to have these tiny steps so that we could actually position the optics very accurately to get the diffraction limit we needed. And they all worked perfectly. So it was a good feeling by the end of this. We were now into L2 and into the orbit after the 3 burns. So during that time, we had 50 major deployments. There were 295 single-point failures on this telescope, which had all been worked through at the point that we got into L2. So all these non-explosive actuators and so on. There was a lot of single-point failures, and yet nothing actually failed to work. Some things didn't quite work exactly the first time, but generally it all worked really well, and we have a great telescope out there. There's actually, in total, there were 344 at launch. There's still 49, I think it is, single-point failures that remain for the life of the mission. So, as in any space mission, things can go wrong that can really impact productivity first, but also, say, if an instrument goes out, or can impact the whole mission, and they remain for the life. So, commissioning now was an extremely extensive series of activities, 6 months, a very tight schedule. I just wanted to give you a sense of this. So there were basically the deployment, cooling, telescope commissioning, and the science instrument commissioning here. And so during that, there was a very detailed timeline of something like 730, I think I say, high-level activities that had to be done with thousands of steps in those. So just, I think as we watch and see and talk about these things, we sometimes don't quite recognize just the complexity of the underlying activities that are involved here. And so optics, contamination control, instrument checkout, whole lots of things went on with a very finely tuned series of activities. So this is one of the charts I just wanted to quickly show without explaining in detail. Give you a sense of the complexity here. This is just cooling down and controlling the cool down of the various components with heaters and the timing to make sure that we didn't put water ice or other chemicals deposited on the mirrors. The folks working this had developed a 246-page detailed plan for what to do, what to monitor, what to do when during the 90-day period. So we're now through into the 60 days in actual L2 where we're doing a plan like this. And it was a bunch of the science team folks who worked this up and monitored. It was a whole 24/7 activity doing commissioning. So now that we're in L2 and sort of while the cool down's occurring, started trying to set up the optics. And so this press release was made February 11th. So this is the NIRCam camera was brought up, the first instrument to be brought up, and photos were taken of the sky. Now, of course, we have 18 mirrors in there, none of which are pointed quite right, and none of which are tilted correctly or shaped quite correctly because there's figure of curvature sensor actuators on the back. And so what was released was said, photons received, Webb sees its first star 18 times. So this was the start of a 6-week period where work was done to make sure that we got ourselves a diffraction limited telescope. A huge number of steps were involved here. Folks, again, working 24/7 during that period, a team of the optics guys. And this is what we got at the end. This was incredible. 2 reasons. One, it's 1 micron. The requirements called for a 2 micron diffraction limit. We halved that. The engineers were so conservative and careful about making sure they met the goal. We did way better, and that is fabulous because science is going to benefit greatly from having really good images down around a micron. It took 6 weeks to do all this, but what was interesting was this was a 30-minute integration just showing this diffraction limit. Astronomers who saw this went, oh, look at the galaxies. Look at the galaxies. These are amazing. And so there was no real science content here. It was just a single broadband image. But it clearly showed that Webb was going to do extremely well for its detection of galaxies. So commissioning completed in this 6-month period. There, as I said, the optical performance was twice as good as required. Everything on the instruments is either meeting requirements or is better sensitivity, etc. Then the telescope system overall, this includes everything on Webb, the whole thing, the pointing stability, the vibration control, the propellant lifetime, what else have I, sensitivity, optics, all these things are better than we expected. It's hard to believe that in a system this complex, as you'll see as you look at some of the other parts, that this actually came about. And it is an incredible credit to the NASA folks, to the contractors around the country and around Europe and Canada, that this actually happened. Project manager did a quick estimate one day and decided that something like 20,000 people worked on parts of this telescope around the world and, you know, in contractors, et cetera, all over the place. And of course, this includes scientists and engineers in all these organizations as well. And it really was a success because of the people involved and their commitment. So just now then to look through what it took to do something like this and where we started and, you know, just sort of what the major steps were along the way. So it started with this really simple-minded concept back in the mid-80s. This was before Hubble flew. And so there was an interesting development here, which started in many ways, I would say, with this simple little comment. Start working on the next big mission. It will take a very long time. And I think having been working on Hubble for quite a while, or what was called Space Telescope then, we sort of recognized that. So this was Riccardo Giacconi. One day he told me, you need to do something on the next mission. We were like 4 years or so, I can't remember exactly when, but 4 years or so before launch. And I said to Riccardo, whoa, Hubble has so many problems. We need to work on that. And he said, just trust me, you just got to do this. You've got to start early because it's going to take a long time. And he knew that from his X-ray days. So a number of us got together and we just started working this up and thinking about, so what could we do that would really make a difference before we knew what Hubble would do? So that was really the challenge. And we had a great bunch of people at Space Telescope Science Institute, lots of young scientists who would come in there. So this was sort of a coffee break, relaxing thing, thinking about the future after you were dealing with some major Hubble problem that morning or whatever. And so what we thought was we really want to go for a big infrared telescope. And we want to put it a long way away so we can passively cool it, no coolants on board, or no active cooling except, as it turned out, for MIRI. So that was where we started, and we kept talking about this, and was this the right thing to do? So here are the key players. There's Riccardo up here. Whoops, wrong way. Up here. Me with some colour in my hair. I was a little younger then. So, and a great team of people. So this is what we were trying to do. So conceptualizing what comes beyond Hubble, before Hubble. And it's interesting to think about that. You know, conceptualizing what you would do now beyond Webb falls in that same category. And there are a number of things that sort of go through your mind. One, you try to think about discovery space. What is likely to enable transformational science that we just don't know about yet? What sort of capabilities would we need? There was a discussion going on very actively by Roger Angel, Nick Wolf, and others about actually finding and characterizing Earth-like planets. This was almost a decade before exoplanets were discovered. So there was a lot of forward thinking here. We were into galaxies in many ways. And at that time, you know, we were looking, high spin rate was here, probing the limits of galaxies in the universe. David Koo who had been working here on his thesis, was there at the Space Telescope Science Institute, and we were talking about different things that a telescope like this could do. And so, as recently I dug this out. This was just an old talk, and we were asking ourselves, so where did the first time that we started talking about what the key science goals were for the next generation space telescope? And it was interesting that what we had already decided, even before Hubble launched, was that galaxies, distant galaxies, were probably the key science objective that we would want to highlight for this telescope, as well as this particular aspect of the challenging exoplanets. So the science that we were thinking of doing was, I think, even then, was out in a place where we would ultimately end up very much so after we saw the first Hubble data. That was interesting that we'd come to that conclusion, and it was really a lot of people contributing to that thinking. So the first big science workshop occurred in 1989. And the lead talk on this was George Field, talking about a lot of the stuff that had been going on in the broader community and the Space Studies Board, et cetera, at that point. So it was fascinating to look back at this. So this was something where we were talking about the science. For example, here is the talk titles of the science talks, with Jim Gunn on distant galaxies, and down there Roger Angel on Earth-like planets, and a whole bunch of other things which are clearly of interest still in many areas now that we would be doing on this telescope, but in a very different time when our understanding of these topics was quite different. But another place where we started to talk about this and what it could do was the 1990 Decadal Survey. There was a panel in there that was looking at future opportunities in space. And one of the things we talked about and wrote up about was doing a 6-meter cold telescope in space, sort of the NGST-like capability. So, and this didn't end up in the final report, of course, because at that point we were desperately, as a community, trying to get CERTA or Spitzer actually through the process and supported by NASA. So that became the primary infrared mission, and it was really premature. We needed to build this case much more strongly, both on contemporary science that we knew was coming up with Hubble, but also technically. But it was just good to go through that exercise and to come up with a rough cost estimate. We estimated at that time $2 billion, and which would be a few $1 billion today, or 4.5 or so, or whatever. But anyway, this will come up again later when we look at some of the challenges with Webb. So there was now interest in the technologies. NASA headquarters through JPL was supporting a program called Astrotech 21. And so this particular conference was really focused on a large infrared space telescope. At that time, we were still trying to build in UV and optical capability, but it turned out to be impractical to do that for a variety of reasons, particularly from a perspective of getting optical performance from a few down 3,000, 2,000 angstroms all the way up to 20 microns. That just wasn't going to work. But the infrared capability was the core of this. We were just trying to broaden its general purpose capability. So passively cooled, 8 meters was sort of the baseline. We started out 10, we were talking 8 here, and obviously far away from Earth so that we could get that passive cooling. So why infrared? This is something I get asked every now and again. And there's, I think, a very simple answer. One is the discovery potential. We knew Hubble was coming along, but it was 2.5 meters optical. We wanted something that was bigger, so we had comparable resolution in the infrared. And we needed the sensitivity, and we gained that both from the size, but also from the fact that the sky, the background in space, is 10 to the 7th less. This is a big factor. And so it's not hard to say, okay, the discovery potential is just going to be out of this world, as it were, when you have gains in the background as large as that. It basically played a very major role in our thinking. So we now launch Hubble launches. It has its problems in the early 90s, but in 95, Bob Williams took his director's discretionary time and took this field. And I think everybody was blown away by what we saw here. All these galaxies in this totally blank piece of sky. So this was a 10-day exposure. We can do that in 6 or 7 hours with Webb now. But this made a great impact on our thinking, whereas we'd been thinking distant galaxies would be a good thing to do. It was, you got to do distant galaxies. There's so much to be learned here. So that became the key part of it, and you'll see that it sort of permeates all the discussions. So during the early 90s, there was an effort carried out by Aura on this report, HST and Beyond. Alan Dressler chaired this committee. It was a very nicely written report, good science case, but it came back at 4 meters. So this I was not particularly happy about. But it was interesting that Dan Golden at the AAS meeting in 1996, so he was the NASA administrator at the time, got up and he said, I see Alan Dressler here. All he wants is a 4-meter optic that goes from half a micron to 20 microns. And I said to him, why do you want such a modest thing? Why do you ask for such a modest thing? Why not go after 6 to 7 meters? And I went, yay, verily, Dan, this is just what we needed. We don't want to be at 4 meters. So he actually then said, we'll do 8. So he set the baseline for the 8 meter, or reset the baseline back to 8 meters. And I was really thankful that he did this. As I note here, I thought 4 meters was too small for the science, and it was politically risky to start out at something so small, because you're likely to end up having to decrease it, to descope it, as most missions are. And so then we would end up with an infrared telescope in sort of Hubble sizes, a few meters. That would not be as good by any means for the effort involved. So anyway, so there was a study initiated at Goddard, and a bunch of people. John Mather was one of the first people to get involved in this. And so 3 studies were led, all now talking about 6 to 8 meters. And so, and for the first time, deployable systems started to be considered as well. Wow, I've been talking for a while, okay. So the formulation authorization document is an incredibly important document in a new mission. This commits at some level NASA to carrying out a program. But one of the challenges was, as you see here, is that it was set for $500 million. Now, we talked about $2 billion for the mission in 1990, but Dan Golden was really into this faster, better, cheaper. So Dan had given us an 8 meter on one hand, and he told us you can have 500 million on the other. So what he gave in one way, he took away at the other, in some sense. So this was a problem. This led to a lot of problems in the future. So then we got to an absolutely crucial step here. So Chris co-chaired the 2000 Decadal Survey, and Steve Beckwith, I don't know if Steve's here, but Steve Beckwith actually was chair of the panel that recommended this to the full survey committee as well. So 2 people from Berkeley played a major role in this, an absolutely crucial role. We must have decadal support for missions of this scale, and we got it here. Now, they were sort of constrained by Dan Golden's $500 million and increased the budget to $1 billion. Well, I think a lot of us thought, now this is going to cause us some grief, and it did. Because, you know, when we estimated $2 billion in 90, that was $2.5 billion roughly at this time frame. And there'd been other estimates around. This was clearly too low, but whatever. At that stage, politically, it enabled us to go forward, but we knew we were going to have to recover from that. So just in a quick thing, so it was obvious what we should be talking about scientifically when it came to policymakers and in public was doing galaxies. Every report that we did just about had galaxies on them for over a decade. So that was clearly the prime goal. So NGST will search for the first light, find the first galaxies, really became the elevator speech that we used in Congress and elsewhere, OMB and all, for why we were actually doing this. So here we are. Why did it take so long to get this? This was now 2001, and so we launched in 2021. So as I said, slowly, painfully, and at great expense. But there were just fabulous people working this. And so that's really why it worked out in the end, even with all the challenges. So it effectively started in 2001. It was realized that we just had to de-scope to get a little more closer to the budget requirements and some of the technical issues. So we took it down to 6.5 metre. TRW was selected as the prime contractor, and they were bought out by Northrop Grumman soon after. And at the same time this selection was announced, the administrator had announced the name. He did not consult with anybody, and he certainly didn't consult with the scientists. So folks who were involved in those days are still annoyed about the way this was handled. But when the administrator came out and said this, there wasn't very much that anybody else could do. So JWST entered phase B and really started working towards the mission. But boy, it was rough. Every year there were budget problems. And so, of course, this got the attention of Congress as well as OMB, the Office of Management and Budget. And so Mike Griffin was the administrator. He came in 2005 and inherited this program. And he said, you guys, you undercosted this from the start. Well, I don't think I ever said to him, maybe other people did, well, you can blame your predecessor for where we are on this one. Don't blame us. Anyway, so the budget increased every year. The efforts to minimize the cost growth were just painful because it was very hard to do. It's very hard to increase the budget very much over the 5-year run out that OMB has set. So there was a lot of great progress. So it was by no means sort of wasted or bad years. But after, even when the project was accepted and put into phase C in 2008, which is really the design and fabrication, and the budget was set at $4 billion in the launch of 2014. Within a year, it became apparent that this was not going to work. And so at this stage then, Office of Management, Budget, congressional support, folks were very unhappy with the way this program was going. So Senator Mikulski, Maryland, strong supporter of Hubble, Webb, and Goddard Space Flight Center, the lead center, was in her district in Maryland. So she decided something had to be done. She wrote a letter to the administrator requesting an independent study. Well, when Senator Mikulski requested something, everybody jumped to attention. And so NASA decided they just had to quickly set up a committee that would look at this and do a thorough job on trying to understand what had gone wrong. And so this is Administrator Bolden, Charlie Bolden, Chris Scalise, John Cassani was chair of the committee. So we had 2 months where we sat down to go through this in detail and try and work out what had gone wrong and recommend what to do going forward. And so we said, look, the budget was too low, sort of obvious. There were not enough reserves to deal with problems every year. The technologies were being developed during the later parts of phase B too late. But often, because the budget was so low, work was being deferred and not being done in the right timing with respect to the project. And one of the things I learned on this committee from the project managers was that has a huge impact on your budget and your ability to plan out. And you can increase the cost of things by factors of 2 or 3 over what it would have cost if you'd done it at the right time. So that was a serious factor here. We went through a very rough blackboard exercise, literally, with the project managers who had a lot of experience on this committee, and said, it's never going to launch in 2014, probably late 2015, and it's going to cost $6.5 billion. But what NASA needs to do is do a bottoms-up cost and schedule analysis to find out what it's really going to take to do this mission. So, and to make sure that when it's done, there are plenty of reserves there to deal with problems every year for the project, for Northrop, whoever. And make sure that this is so important for NASA. As you know, the word was existential threat to NASA, and it wasn't entirely true, but it was true in the sense that if this had failed, it would have hurt NASA's budget. And so to, folks in NASA, that's pretty getting existential. So report directly to the administrator's office. NASA accepted every one of these recommendations. But of course, when the Office of Management and Budget saw our cost and launch estimates, they got really worried too. So they were very unhappy. So NASA really stepped up to the plate and did a very thorough replan, put in a new program director at headquarters, a new project manager at Goddard. So a bunch of people were changed out and did a very careful and thorough analysis of what it would take to do this mission. It took many months actually to get that information in and to run it through these statistical JCL models, the joint cost and schedule confidence level analyses that would actually only just come into being in the sort of few years before that. Prior to that, the analyses were done very differently. So what they came up with was launch in 2018, late 2018, $8 billion. That was a huge increase. And what they said is you've got to get us on track now with the required budget or it's going to cost even more and take longer. So when the Office of Management and Budget and Congress saw this, so here is the budget profile that the JCL recommended. The red one, here is what NASA had planned and OMB had planned. So it's essentially almost a doubling here. So a lot more money. So you can see why these folks were all unhappy. Getting folks on board here was not easy. So this came out in May of 2011. July 7, 2011, July 6, I heard a rumor that it was going to get killed. July 7, Chairman Wolf of the House Appropriations CJS Subcommittee, Commerce, Justice and Science, said $4.5 billion for NASA science programs, which is $431 million below last year's level. The bill also terminates funding for the James Webb Space Telescope, which is billions of dollars over budget and plagued by poor management. So this was really worrying. So at that stage, we were trying to find out what it was we should do here. Folks who had been in Congress and worked these things said, you've got to take this really seriously. And there are people in NASA who said, oh, Senator Mikulski is going to recover it for us. They said, don't trust to that. These things, you don't know how it's going to work out. You have to work this. And so we did. So John Mather put together a letter from 32 Nobel scientists, Nobel Award winners, recommending going ahead with this. There was a lot of effort a lot of disinformation was being disseminated by some folks who wanted to see Webb die, thinking that they were going to get the money for other programs. Wrong. But anyway, so we did a lot of effort trying to make sure we countered this disinformation. So it's not new that we have disinformation pushing our lives around. So we got great support from physics societies. And I think because a lot of folks remembered SSC and didn't want to have that happen again. But there were senior astronomers who were going to Congress and saying, kill this. It's badly managed. We'll use the money for something better. So what they didn't realize was that when you kill things like this, Congress does not allow the money just to go to NASA to be used for whatever. The $431 million disappeared from NASA's budget, in Wolf's budget. And so you're running a real risk saying, kill this, it's not good to do. So even the American Astronomical Society did not support this very much. It was really physics and planetary societies that gave us the greatest support. But interestingly, I think what really helped us was scientists giving support is necessary but is not sufficient. What you need is a broader ensemble of folks, and we had that. Amazingly, I didn't know that there was so much interest in Webb years before launch around the country. There were planetary societies, amateur astronomers writing, we had school kids writing in, teachers. As I said here, I got a email from a teacher in Kansas saying, how can we help? This is amazing. I hadn't realized that this new telescope had actually permeated and folks were aware of it. So we were lucky that there was this level of support there. Wolf saw it and thought, okay, this is interesting. Mikulski was working it internally, and they came to an agreement in the conference committee language later that year in the budget discussions and agreed to put it back in. And so is Senator Mikulski with Chris Scalise at Goddard So that got it back in the budget, but of course OMB and Congress were going, we don't want to fund $8 billion for that. Well, you just agreed to do it, so you're going to need to ramp it up and do it. So it was a back and forth on the budget for a while, but it did come about. And just a quick summary here. I really think that if there hadn't been a number of things that had come together at this point, like a hard-hitting ICRP report that was very honest, the response from NASA saying, yes, we will do it. We'll do what it takes to make this work. The very careful and thorough budget study, and then the support of scientists and the public, then I think we got it back. But if that hadn't happened, I think this would probably have gone the way of the SSC. So we were lucky. And as I said, the budget would have disappeared from NASA. So science at NASA would have lost billions of dollars as well. It's hard to keep those. So we had a pretty good period then that continued now for the next 5 or 6 years. The telescope and its instruments were being put together at Goddard Space Flight Center. And so it was just delightful when I saw this sitting in the clean room. You see this sort of finished optics and so on. That was great. So in parallel, the sun shield, the spacecraft, the cryocooler are all being put together out at Northrop Grumman in Los Angeles and Redondo Beach. And so there were 2 parallel paths of major activity going on here with this system. And an absolutely crucial part of the development of this was to make sure that we had the optical performance in space at the temperatures that we were going to be operating at. We did not want another Hubble situation where we launched and the optics were not exactly what we needed. We couldn't go back to Webb, not like Hubble. We could go up and replace instruments and correct for the optical problems in the early 90s. When this is sitting at L2, that's it. So there was a huge chamber that was used for Apollo that was sitting just full of junk and so on down at Houston at the Johnson Space Center. And the project spent, I think, something like $100 million to refurbish and make this chamber work fully so that we could put the whole telescope and its instruments in there and verify the optical performance and everything else that was associated with that. So there was what's said here to be a 90-day test. As it turned out, it was 100 days in the end. So here is, I'm not going to go through this in detail, of course, just another one of those things to give you a sense of just the level of planning and activity that's required in a project like this. This was 100 days, cooling down, and of course you had to worry about the contamination again to the issues there. They played a lot with that as well. Not quite so critical because you could clean things, so it was harder with the finished optics. And so they went through, and I looked at they had a dynamic plan on the computer. I looked at a page of that. They had parallel activities laid out in 10-minute segments for 100 days. And folks are working down there 24/7. So this was just an incredible example of the detail and the level of commitment that's needed to do a project like this. But what's interesting was Hurricane Harvey whacked Texas in the middle of this. It hit further west and then looped around and dropped, I think, something like 20 inches of rain on Houston in 8 hours or some ridiculously short period. So everybody who was running this test had to bunk out at the test site. They got in air mattresses and they were sleeping there, eating there for several days because they couldn't get in and out. And then there was a problem. The liquid nitrogen supply was running out. And so they feared that they may have to warm the whole thing up, and that would have added a whole bunch of time, having to come back and start up the test again. So one of the guys down there eventually found a company that was willing to send a liquid nitrogen-filled truck through 3 feet of water to the center to fill up the liquid nitrogen tanks. So they were very entrepreneurial in dealing with this, and they found a great company and a driver willing to do it. So anyway, the test went well, and it really demonstrated that we had a good telescope here and the instruments were as we expected. Okay, thanks. So here is the sun shield at Northrop. So 5 layers of this flimsy stuff are what we actually deployed in space and absolutely crucial to the performance of Webb. This is, 1 mil, thousandth of an inch thick Kapton, coated, and these things have to be located 2 millimeters. So this is, to me, this was the biggest challenge that we faced. I walked around the full-scale engineering model, and this is, it's 20 meters by 14 meters, tennis court size thing, at Northrop Grumman, and saw all the cables that operated. Oh, let me move on one. So there's 139 release mechanisms, 70 hinges, 8 deployment motors, 400 pulleys, 90 cables, quarter of a mile of cables on this thing. This all had to work to make this sunshield work. And when I walked around that, I thought, oh my God, we're going to launch this and expect it to work. So there were lots of problems. Things went wrong, deployments went wrong, cables got tangled. Northrop did a phenomenal job on this. And I think even though this sort of doesn't quite get the recognition that a lot of the other aspects do, I think this was numero uno engineering challenge for this project, was making this work. Soft structures are just hard to predict and model. And the guys, they did great. So we had a sun shield. So finally, from here is the Otis, the telescope assembly that's come back from the test at Johnson. The assembly of the spacecraft and sun shield that was being put together at Northrop. And they had to be joined up eventually. And so you'll notice the date. This came back in 2018. We'd committed to Congress we were going to launch in 2018. So we already knew in 2017 that we had a problem here. So we had to go back to Congress and say, we have a problem, folks. We need $800 million more. And they were, no, not again. So at this point, I think folks sort of went, just don't do it again. Spend the money, do it, and make sure that you get it finished off. And that's what we did here. So the next couple of years, there was a huge effort to team the folks from NASA and Northrop Grumman. NASA people started living at Northrop Grumman and working together. And it was interesting. I think the two different engineering cultures came together and actually teamed, and really there was a synergistic approach to problem solving that was actually very important. There's a key lesson learned here, that you just, if you've got different folks who do things differently, bring them together. You think differently about problems. Anyway, we got to launch and it was great. So then at that point, this was last year, the observations started coming in, the early release observations, and this was in Baltimore in the auditorium. I realized sitting there that this is exactly the same auditorium that we sat in 33 years before to do the conference, the 1989 conference about Next Generation Space Telescope. That was sort of a strange deja vu situation. Didn't look all that different other than the electronics were slightly more advanced, if not significantly. Anyway, so this is where we were at with the telescope last year. And so I did have some astronomy results slides I was going to show, but I think I've used up the time, haven't I, pretty much? I don't think there's anything. Yeah, so basically, I will skip the science at this point. I'll make the slides available so you can see what I think about the early galaxy situation, and you can ask me some questions if you want about it. So let me just jump to my sort of closing slides here, if I can actually do that. Oh yeah, right. So this is my bottom line, and I can happy to chat with you or email with you about why I get to this. That the problem with the very early galaxies that has been discussed a lot, science, media, wherever else, I think that we are not thinking carefully enough about what we are seeing. What we are seeing is light. We don't know the masses of these galaxies. We are making assumptions and doing the transformations that apply well at later times in the universe at the early times. And I don't think we do not know that they work for these early galaxies. And so there are other things that are folding in here. The existence of active galactic nuclei, the very early population 3, the low or zero metallicity populations are all potentially in the mix here. And so I think some of the things you've seen have sort of been people jumping to conclusions and ignoring, our favorite Occam's razor approach, which is take the sort of simplest approach first and see if it works to solve the issue. So at this stage, I don't see this area really challenging lambda CDM cosmology. It could do so at some point later, but I think we need to understand much more about these galaxies. And I would just love to see dynamical masses using velocities to get a mass in these galaxies. That would be good to do. So we're getting a lot of great data. So let me I think the science promise is really being realized and has been realized over the last year. There's been a phenomenal amount of information. It's incredible to see the number of papers that are coming out here on so many different areas. And this is just galaxies. There's exoplanets and nearby galaxies, star-forming regions, you name it, are playing. There's lots of information out there. And of course, web now is a really part of our culture, amazingly so. This was a photo that went around from Halloween last year. She put this on the web, on social media somewhere. And it was just, this is sort of everyday things that we see so often from folks. They're just entranced and interested in web. And so that feels good. I mean, I think from a science perspective, the fact that we're touching the sort of heart and interests of folks all across the nation is just wonderful. And so just now to the last slide. So just started. There's so much to come on web. And so interesting times await us. So thank you very much for all the time. This is not my area. We always had talked about, especially after they were discovered in the 90s, that web would play a major role in helping to understand what we are seeing with exoplanets. And I think we're seeing that, but I think I'm not the person to ask for a summary about what the major discoveries have been. Sorry, I do galaxies. But, I'm really interested to see what it does. And it is impressive, the number of news releases, stories that I see go by.
It's just been overtaken by all these other exoplanet observations.
Sorry, what has?
Well, an nasty possibility, maybe it's just been overtaken by all the other observations. All the other exoplanet observations.
Well, there is a lot, there's no doubt. And putting it together, that's one of the challenges that we face in any of these areas at the moment. There's been so much data coming down, trying to put this into a package to understand what is this telling us about this particular aspect of the universe that we would like to understand. And so exoplanets, just as in galaxies, I think we're sort of, what's going on here? They have some of the same situation.
So at the back?
Yeah. Could it be possible that coming from now that we can see these galaxies that God created at the beginning, and we can just now see them?
No, so, we're seeing them as a snapshot in time, but unfortunately, we have a wonderful sort of statistical ensemble that we can look at and describe through time. So one of the key science goals related to these galaxies was seeing the assembly of galaxies or understanding the assembly of galaxies over time. We do that by taking snapshots. Actually, when you look at one of those images, like the Hubble Deep Field, like the cluster, you're getting a history of the buildup of galaxies over time in that one image. And so when you spread that across hundreds of these images, we have an amazing sample to work out sort of how galaxies are growing and changing with time. So this is going to, I think, provide us a lot of insights in that area, not just on the first galaxies or the earliest galaxies, but also how we understand what happened between then and our Milky Way now.
Okay, Roger?
I assume there's one focal plane for a reflective mirror like this. How do you field multiple detectors in multiple spectral ranges?
if we put the apertures around the focal plane. So it's a, a wide field telescope. So the instruments are set up to see different parts of it. I had a slide, but I thought, oh, it's getting too many. So I took it out. But yeah, so each of those instruments has a different part of the focal plane. And because of the optical performance of this coarse design, every one of those fields is really good optically. So it has the diffraction limited images. So there's, I think there's something like 5 or 6 areas these instruments fill in, because some of the instruments have double cameras and so on. Yeah, Hubble does that too. It's just the same as Hubble. Uses different parts of the focal plane.
Yeah, Bruce?
What about signatures of the very first stars? There was a paper, a single band in Spitzer, which I believe looks at the background and the statistical fluctuations in plane detection of the first stars. And that remains controversial. So how is Webb sort of going forward on that?
Yeah, this is interesting because I think that getting that same data from Webb would be good. You've now got more sensitivity. I don't think you really need resolution so much as you just need to get a good deep image where your characterization of the fluctuations can be made very accurately. The calibration issues we've had with Webb and the difficulty processing the data, I think probably preclude that currently, but we'll get there. At some point, we'll get these damn telescopes fully calibrated. It's just, it's tricky because there's a lot of effort to do that. And then I think going back and doing that experiment again would be great because you just have so much more sensitivity here. I mean, I don't think that, I don't have a strong opinion about that. It's a very challenging observation. And I don't think the interpretation is also challenging as well. Yeah, yeah, the background effects or foreground effects are horrible.
How do they decide what to look at?
There's a
Well,
proposal
could you repeat
process.
the question?
Sorry. Yeah, we decide what to look at through a proposal process. So every year, you put in fact, the next deadline for proposals is late October. So, and they go to time assignment panels and committees, and the folks there choose the proposals that they think are the best, and they're the ones that get done. Typically, the oversubscription was small at cycle 1, like 10 times last time, and I expect it will be large this time. So yes, it's proposal driven and science driven, really science driven.
Yes?
What do you think should be the goal for the simulation of telescopes after Webb?
So this is pretty much the next
repeat the
telescope
question.
after Webb. Yes, so the next telescope after Webb is interesting. So for a long time, there have been discussions going on in the community. We held workshops back in 2003, I think. It was the first one that was organized on this topic is what do you do next after Webb? So we're always thinking ahead. And what the Decadal Survey did in 2020 was recommend a telescope that would be optimized for searching for planets and characterizing them, particularly with an interest in Earth-like planets. This is extraordinarily hard to do. But so there's a project, if you look up, what is it? HWO.
Yeah.
What is it?
Habitable Worlds Observatory.
Yeah, Habitable Worlds Observatory. I forgot the acronym for a moment. I'm so used to I just deal in acronyms. But if I have to actually spell them out, my brain doesn't have it. So yes, Habitable Worlds Observatory, HWO. It wasn't called that in the Decadal Survey, but that seems to be what NASA is now talking about. And that's a 6-meter telescope, not unlike Hubble in its optical coverage, but with incredible precision optics and stability that's required to suppress the light of the star by 10 to the 10th to make sure you can actually see the planet out there and measure it.
Yes?
I was just wondering, along these lines, are there some areas of the space that is more interesting than others?
Yeah, so it's, I...
That's with the great walls and the bubbles and all that.
Yeah, so the question was about, are some areas of science more interesting than others for a telescope like this? I think, we're driven with what we do with these telescopes on a bottoms-up process from the community. So it's what people propose to do that drives it. Now, of course, you know, there's sort of fads. You go through periods where particular areas of science are really interesting. You get a lot of proposals in that area, and then you get some results and people have trouble. What the hell does this all mean? And then it sort of flattens out a little bit and other areas grow. So it varies and
That's what I
changes.
mean, like what areas?
So at the moment, I would say most of the proposals, exoplanets are extremely popular. Distant galaxies are very popular. The assembly of galaxies, so looking back at galaxies over the life of the universe, would probably be the two biggest ones, I would say. But I haven't actually looked at the statistics, but I suspect.
Points in space more interesting?
Sorry, which?
Points in space, like looking at where the great walls converge.
Yeah, different directions.
Yeah, there's sort of different areas, and so those sort of issues about how the galaxies cluster and so on will come out of other proposals as well. When you do a wide area survey with a telescope like this, you get information like that almost for free, as it were. So these big images can actually do a lot of different science as well, too.
Yeah.
Is there like real scientific reaction to that much?
Sorry, is there?
Is there any like repair plans?
Yeah, so the question was about repairing it. No way. So the only thing that we thought about was actually putting a valve on the bottom so we could put more propellant in it. As it turns out, we don't need to really do that. So there is no way we can really repair this telescope. One, we don't have the current technology, and even if we did, which we may get in 10, 15 years to actually go out there, it's extremely sensitive. You know, you move it, you whack it in some way with all that sun shield and all the rest. This is not a telescope that was designed for repair. And of course, things are built in, well into the system. So you have to take the decision right up front. I want a modular telescope. I want them accessible from the outside. I want grappling hooks. I want simple release mechanisms. I want simple power and coolant plugs or whatever. All these things play into the design. Webb was never designed that way. So for all practical purposes, it's unserviceable. So better keep working.
Okay, let's thank our speaker again.
Thank you very much.